Hello, welcome to my talk on monitoring latencies. How fast is your REST service? So a few words about me. So who am I and why am I standing here talking about latencies? So I'm Fabian, I work at Grafana. I'm also involved in open source, so I'm a member of the Prometheus team where I maintain the Prometheus Java metrics library. What are we going to do in the next 45 minutes or so? So I thought it's a good idea to write the table of contents as some kind of Java code. Don't know if that was a good idea, but anyway, so this is how you would measure latencies, right? So you want to know how long something takes. So you take a start timestamp, do something, and then eventually you can calculate the duration by taking the current time minus the start timestamp. And then you observe the duration in a data structure that's good for observing durations. And the most part of this talk will be about different ways of representing durations, what data structures you can use, and what you can do with different representations in your monitoring backend, in Prometheus, for example. But I want to start with a quick demo on the first few lines of code here, actually measuring durations, because even though this is obvious, there are a couple of pitfalls to be aware of, and I think it's good to start with that. And once we have seen the kind of common pitfalls with observing durations, we move on to exploring different data structures. So my demo is this nice little REST service here. So it's as simple as it can be, standard Spring Boot Hello World REST service with the current Spring Boot version. So it sleeps a second, then responds with hello. So we expect latencies to be like 1 second. What we do not see here is code actually measuring the duration. And the reason is that you do not need to write this code explicitly in Spring Boot. I just enabled the Spring Boot actuator framework. And under the hood, this comes with a metrics library named micrometer. And this will just measure these durations for me, right? And I also configured this thing to expose the metrics in Prometheus format. And I have Prometheus and Grafana running on my laptop. And if we look at the latency graph, it looks like this. So a straight line at 1 second. What we are seeing here is the average latency, and average is not a good way for representing latencies, but for this demo, it doesn't matter at all. It's just, 1 second. And the actual load is coming from a little client that I wrote. So this thing starts 10 threads in parallel, and each thread has an infinite loop just sending one request after another. We see in the output here that it's already running, and each request takes 1 second. So far, this is boring, but it will soon become interesting. So what we are going to do is we are going to stop this and increase the number of threads from 10 to 400. And if you already know what will going to happen, I think you're pretty good, because for me at least, that's not obvious at all. So let's try it. So what we are seeing now, so it starts quickly with 1 second latencies, but then over time, the latencies go up, and now they are up at 2 seconds, right? So basically my performance decreased. It's now 2 seconds per call. But the interesting fact is if we look at our server-side monitoring, we don't see any of that. So there's still a flat line at 1 second latency, and there's no indication that my client actually waits longer. And this is interesting. Like, why do we see like different server-side metrics than we actually see on the client side here? And the reason for that is a principle that I'm showing this with Spring Boot here now, but that actually applies to a lot of monitoring scenarios, which is the difference between service time and response time, right? So in order to understand this, you have to know how Spring Boot works. So Spring Boot by default starts a built-in servlet container named Tomcat. And Tomcat will have 200 worker threads, and these threads are sitting there waiting for requests to come in. Right? And as soon as a request comes in, a worker thread takes this request, passes it onto the Spring framework, and the Spring framework will service the request. Right? So what happens if all 200 threads in Tomcat are busy? Then if the next request comes in, it is put in a queue and it waits until a worker thread becomes available. So, and as soon as a worker thread is available, it takes the request, passes it onto the Spring framework, and the Spring framework will service the request, right? So from the point of view of the Spring framework, everything still takes a second, right? So from the time the Spring framework gets the request and processes it and so forth, it's really just 1 second that the Spring framework takes serving the requests. The Spring framework has no chance to see that the same request was actually sitting in a queue in the Tomcat container for another second before it was actually handed over to the Spring framework, right? And this is the difference between service time and response time. So what we typically see if we look at server-side metrics is the service time. It's the actual time that a server spends processing requests, right? The response time might be different if there are some queues in your infrastructure that add some additional time before that. And I'm showing this now with Spring Boot, but that's not, specific to Spring Boot. So you can have whatever components in your network infrastructure that queue requests, whatever, some load balancer or some Kubernetes networking or whatever you have, right? This is just something to be aware of. So if you have the chance in your monitoring to look at client-side metrics, so that's a good idea because then you would look at the client-side data and see that this is actually different from your server-side monitoring. Sometimes you do not have the chance, and then it's at least good to be aware. So if you look at server-side metrics, in most cases it's the service time you are seeing. And if you have additional queues before the requests end up in the server, then you need to add them if you want to see the actual response time. So that's the first common pitfall when measuring latencies. There's a second one that I can show with this example. It's also interesting. So imagine you are aware of the fact that your response time might be higher and so forth. And now you write a little load test like the one I wrote here in order to figure out how bad it is, right? And now you look at the output and you see, okay, my latencies increased from 1 second to 2 seconds. That's not great, but for my service, it's still enough. This conclusion would be wrong. So the output of this type of load test is highly misleading, right? And the reason for that is in the way I implemented the load test. And that's not only me doing something stupid here, but this is actually how many load test tools also work. So it's important to understand what your load test tool actually does. And what this does here is it starts 400 threads, and each thread has an infinite loop, just sending one request after another. So what happens if all those 400 threads are busy? All of them have sent their request and wait for response. Then basically my load test will stop until the server catches up and sends the next response. And only when I get the next response, there's the next iteration of the loop and I send my next request, right? And so basically the effect of this is as soon as my server is at its limit and doesn't respond anymore, my load test slows down, right? So basically a load test that backs off as soon as the server is at its limit. And that's typically not what you want to see if you want to understand the behavior of your service under load. So I have another version that's better. It's here, this one here. This one here just sends 400 requests per second, but doesn't wait. It just sends out 400 requests per second no matter what. So if I just start this instead, we will see totally different behavior, right? So we will see that initially response times are about a second, and then requests start queuing up, and it's now already up to 4 seconds. And these response times will just increase until we start running into timeouts, and then we see a couple of exceptions here. So this is more likely the type of thing you want to test. And so if you use load test tools or write tests yourself, just be aware, try to understand what your test actually is doing. And if it has kind of a certain number of parallel threads and that limits it, you might have a load test that just backs off as soon as the server is at its limit. So, and actually, funny enough, if you now look at the server-side data, you're monitoring this, it's still all fine, right? So you have no idea that actually there are clients now waiting for 18 seconds. So anyway, and here are the timeout exceptions. Nice. So that was a quick introduction on measuring durations, what time interval you measure and what are common pitfalls. So we talked about two things. We talked about this difference between response time and service time. So if you have server-side metrics, often these are service times and not response times, and this is something to be aware of. And the second thing is, if you try to load test this and figure out the behavior of your service, then load tests might back off when your server is at its limit, and that's not. Then if you look at the results, then be careful with interpreting what that means. So that was the first part on actually measuring durations, being aware what you are actually looking at. And now to the second part, data structures for representing durations. We will go through a couple of different representations. So we start off with average and maximum, not because they are particularly good, but because these are the things, if you have a standard Spring Boot application, you start the enable actuator and configure nothing else, then this is what you will have by default out of the box. And therefore, I think it's relevant to mention it and to make sure you understand what you can do with that and what the drawbacks are. Right? And then there are other representations that you can enable. There are percentiles, there are histograms, and there are even new types of histograms that currently only exist in experimental feature branches, but that are being developed both by the Prometheus community and by OpenTelemetry. And so it's looking very likely that they will be adopted once they become stable. So I want to give an outlook on that as well. I wanted to give this a bit of a structure, and so I came up with evaluation criteria that we will look at for each representation. So what I came up with is these three here: time interval, aggregation, and practical value. So time interval is basically, this is also something good to keep in mind. If you talk about latencies, you always talk about a certain time interval, right? You have an average latency over the past 5 minutes, or an average latency over the past 10 minutes or so. So it only makes sense if you think of a time interval. And some representations allow you to specify this time interval at query time ad hoc in your time series database. With some algorithms, it just comes pre-calculated from your instrumentation library, which of course is less flexible because you cannot adapt this easily, but also it's sometimes really hidden and you don't even know what time interval you're looking at. So that's one difference between different algorithms. The second one is a lot more important. It's aggregation. So that basically means if you have scale out your service, you have multiple instances, so server A, server B, server C, then you get your latency numbers from server A, from server B, from server C. Can you aggregate them and get total latency numbers across all your instances? With some representations, this is possible. With some, it isn't. And this is very obviously relevant for distributed applications if you have multiple instances of your service. But this is also relevant if you just have a single instance, because often you end up getting different latency numbers with different parameters. Like, for example, one latency metric per REST URL, or independent latency metrics for good cases and error cases and so forth. So even if you just have a single instance, you might end up with multiple independent latency metrics, and it's good if you are able to aggregate them and calculate total latency values, right? And then the last one, how valuable are they in practice for monitoring REST services? That's more my opinion, I would say. So the first two are actually hard facts, so there's nothing to discuss about. Whether or not something makes sense in production monitoring, I want to share my opinion, but it's fine if you have another opinion, okay? So let's get started with the average. So as I said, this is what comes also out of the box if you just enable the actuator in Spring Boot and expose it as Prometheus metrics. And the first interesting thing here is that you do not see a metric named average, right? So you see two independent time series here. One is the sum, or the full name is HTTP server requests seconds sum, right? And the other is the count, HTTP server requests seconds count. And the sum is basically the sum of all observations. So whenever you observe duration, you add it on top of that. So it's the total time spent serving request, all summed up, right? And the count is the request count. So whenever there's a new observation, you just add 1 to the count, right? And obviously, if you have these two, so if you have the total time spent serving request and you have the number of requests, you can divide these. So the total time spent serving requests divided by the total number of requests, and then you can calculate an average. Then you have the average time per request, right? You can also do this for specific time intervals, and that's what's shown here. And that's also, by the way, an example of a Prometheus query. So if you have not seen Prometheus queries before, that's how they look like. So basically it says, I'm looking at how much did my sum increase over the past 5 minutes. So that's the time spent serving request over the past 5 minutes, right? How much did my count increase over the past 5 minutes? So that's the number of requests over the past 5 minutes. And if you divide these two, then you get the average response time over the past 5 minutes. So that's how this works. Question, of course, is why is it so complicated? So why don't I just get an average latency that I can use, right? And the answer is aggregation. So there is like a golden rule in latency mathematics, if that even exists. You cannot calculate an average of averages. So if you have an average latency from server A, average latency from server B, and average latency from server C, and you try to calculate an overall average across all of them, that's just mathematically wrong. So you cannot do this, the results will be wrong, right? However, if you have a sum and a count, then there's something you can do. So if you know the time spent serving requests in server A, you know the time spent serving requests in server B, and you know the time spent serving requests in server C, you can sum them all up, and then you have the total time spent serving requests, right? And the same with the count. So if you know the number of requests that were processed by server A and the number of requests from server B and the number of requests from server C, you sum them up, you get the total number of requests. And then if you divide these two sums, then you get like an aggregated average. And that's the reason why Spring Boot by default and also other libraries or other frameworks tend to split the data for the average metric up into an independent sum and count time series, so that you have the flexibility in your monitoring backend to aggregate them before you calculate the average. Okay, so if we look at the criteria, so actually, like from the hard facts, time interval and aggregation, it's looking quite good. We can specify the time interval ad hoc. Aggregation is possible, as we have seen. However, the practical value of average metrics is pretty limited. So they have some practical value because they are available by default. So that, of course, gives them some value. But the problem with averages is they are heavily affected by outliers. So I put some numbers here as an example. So if you have a service that's really precise and just answering every single request in 20 milliseconds, right? And you have 1,000 requests coming in, and each of the requests is just 20 milliseconds, 20 milliseconds, 20 milliseconds, very stable service. And then you have a single request where whatever, the client dies and it doesn't read the response, and so this hangs for 30 seconds before its time's out. Then if you calculate the average of 1,000 times 20 milliseconds and 1 time 30 seconds, you will end up with 50 milliseconds average. However, if you see these 50 milliseconds on your monitoring dashboard, it doesn't tell you much about how your service behaves, right? You see 50 milliseconds, but nothing takes 50 milliseconds. So you don't see that 99.9% of your percent of your calls are actually served in 20 milliseconds. You don't see about the outlier. It's just really hard if you just see an average latency to conclude how your service actually behaves. And that's the reason why averages are not very popular when setting up monitoring dashboards. Okay, so the second one that comes out of the box in Spring, for example, is the maximum. So that's a quick one because it's really straightforward. It just comes as it is, pre-calculated maximum provided by the library. Aggregation of maximum values is really trivial. So if you know the maximum from server A, maximum from server B is maximum from server C, you just take the maximum of them and then you have the total maximum. So you can take maximum of maximums. That's trivial, right? And there's of course also a max function in the Prometheus query language to do that. The evaluation is a bit more interesting here. So unfortunately, maximum values need to be pre-calculated in a library. That's nothing you can do in any time series database. Spring Boot, my micrometer, which is part of Spring Boot, I think has a default time window of 3 minutes here, which you can configure. Other libraries might have other defaults. Aggregation, as we have seen, is trivial. And the practical value, I don't know, maybe something that's more interesting to discuss. So I think if you have load tests in mind, then it's definitely valuable to look at the maximum, because if you run a load test, you want to understand the worst case behavior of your system, find the slowest path and so forth, and having some information like what's the slowest call that I observed during my load test, that's definitely a good thing. For production monitoring, I'm not so sure. So, I mean, if I think of this practical value for production, what I have in mind is I'm on call for a service running there, right? And I have the pager. I go to bed, place the pager next to my bed, and I ask myself, do I want to be woken up in the middle of the night because this metric is above a certain threshold, right? And the answer is for maximum values, I certainly do not want that, right? So if my service is doing great all the time, and then there's one outlier that for whatever reason takes long, and it doesn't happen again, after that everything's back to normal, after that everything's great, I certainly do not want to be woken up in the middle of the night and try to figure out what happened. I even think I don't want to spend a lot of time the next day to figure it out, right? Whatever, maybe some network packages dropped and something typed out. It's not the most important thing in my opinion, right? If you're interested in that and also want to hear more opinions about maximums, I have a recommended talk down here. It's by Gil Tenne, who is a real expert in latencies, and he's doing latency talks for many years. He has one that's called How Not to Measure Latency. So it's on YouTube. You can Google it, find it. It's interesting. It also inspired some of the demo that I showed in the beginning. And also he has strong opinions on maximums. So if you want to dig deeper into it, definitely a recommended video to watch. So that were the two metrics that come out of the box in Spring, average and maximum. Both, in my opinion, not too great, but better than nothing. So, and now something that I really think is great, which is percentiles. So I think everyone knows what percentiles are, like how they work. So I have an example screenshot here with the 50th, 95th, and 99th. So the yellow line is the 95th percentile. That means 95% of the calls have been faster than that, 5% of the calls have been slower than that. And I think this is really relevant information. So if I told you about maximum, so if there's a single one-off call that took longer than everything else, I might not be too worried. But if 5% of my calls take longer than expected, then there's certainly something going wrong, right? That's what I really want to know, and that's what I want to investigate. And depending on the service level, it might even be the 99th percentile that's relevant, or the 99.9th. So depending on how important the timing of your service is. But this is not about single outliers. This is about a certain percentile of your latency being slower than expected, and this is something that almost certainly has something to do with your service or the infrastructure around it and so forth, and where it's worthwhile figuring out the root cause. Okay? If you want to use percentile metrics, I think it's interesting to, you don't need to know exactly how algorithms work that maintain percentiles, but at least to have a bit of an understanding. How much does it cost you in terms of memory that you need to spend in order to track these percentile values, right? Because if you think of it, the straightforward way and the only correct way to actually calculate percentiles is you have a sorted list with all observations that ever happened, right? So whenever a new duration is observed, you put it in that sorted list. And then, like, if you want to query a percentile, it's very easy, right? If you want the 50th percentile, it's the entry in the middle. If you want the 95th, it's the entry at position 95% of the list length, and so forth, right? However, if it was implemented that way, then you would at some point run out of memory, right? If you just keep each observation that you monitor in a sorted list, the sorted list would just grow indefinitely, and you would at some point run out of memory. So there are algorithms to prevent that, and what they basically offer is a trade-off. So you do not get the exact percentile, but in return, you use a lot less memory. And what I'm going to show you now quickly is the one that's implemented in the Prometheus Java client. And then later, when we have talked about histograms, I can show you what's used in Micrometer that's part of Spring Boot, so that you have two examples of that. So the one in the Prometheus Java client, it's called CKMS, which is the first characters of the last names of the authors of the corresponding research paper. So I put it on the bottom of this slide. And the idea is basically when you specify percentiles, so I have a code example at the top right where I specify the 50th, the 95th, and the 99th as the ones I want to have. But you also specify an error margin. So for the 50th, I accept 1% error. For the 95th, I accept 0.5% error. For the 99th, I accept 0.1% error. Okay, so basically what that means, you don't get the 50th percentile, you get something between the 49th and the 51st. And now this algorithm can go ahead and throw away observations if throwing away the observation means that you still do not violate this upper bound for the potential error. And I did an evaluation to see how good this is. And I'm actually impressed that it works pretty well. So I ran this starting with 1,000 observations and going up to 100 million observations. I started with a single percentile, just the 95th, up to 3 percentiles, 50th, 95th, and 99th, also with quite tight error margins, so just 0.1% error for the 99th or 0.5% for the 95th. And the numbers you see here is the number of observations that you need to keep in the list. And interestingly, it doesn't grow. So like if you add another 100 million observations, at some point, it's just stable. It doesn't grow anymore. So that's pretty good news. And order of magnitude is, I would say, about 100 values. So you need to store about 100 double values in memory to track such a list. And that's not too much. I mean, 100 double values, that's really an amount of memory you can spend. So it doesn't hurt to include these types of percentiles in different places of your code where you're really interested in measuring your latencies or understanding the latency behavior. Okay? So if we look at the evaluation of percentile metrics, actually the hard facts look pretty bad, unfortunately. So it's not possible to specify any time interval at query time. So these algorithms produce pre-calculated percentiles, and they produce it based on a time interval that you have implemented there, right? And unfortunately, aggregation is also impossible. I told you at the beginning, you cannot calculate an average of averages. And in the same way, you cannot calculate an average of percentiles. So if you know the 95th percentile from instance A, the 95th percentile from instance B, 95th percentile from instance C, there's no mathematically correct way to somehow aggregate them and get your total 95th percentile. It's unfortunately impossible, right? And yeah, this is actually bad because the practical value of percentiles, I think, is pretty good. So you can, define what for your specific service is a relevant fraction of the calls that you want to measure. You can use this for service level objectives. You can use this for alerting. It actually is a great number for monitoring, right? But this lack of aggregation is a bit of a bummer, I would say. So one thing that solves this lack of aggregation is histograms, but it comes with other issues. So that's that's always the case. There's no golden bullet, I guess. So histograms, I think everyone knows how they work, what they are. So you have buckets, in this example, between 50 milliseconds and 75, between 75 and 100, and so forth, and you just count the number of observations in each bucket, right? And the great thing about histograms is if you have two of them, given that they have the same buckets, of course, you can just sum them up, and then you have a total histogram aggregated across two histograms. And that's also very easy to do in the Prometheus query language. It's just very straightforward. So that's one awesome property of histograms. There is another thing that makes them even more awesome, which is that you can estimate percentile values based on histogram data. So if you, for example, with this data that's on the slide here, are interested in your 80th percentile, right? You would just count the observations, and then you would be able to figure out that it must be somewhere in this bucket between 200 milliseconds and 225 milliseconds. You will not be able to know where it is in the bucket, but you find the bucket where it is in, right? And like the most trivial thing you can do is you just take the middle of the bucket as an estimation, and then you have half the bucket width as a potential error, but that's good enough for many cases, right? And there's also a built-in function in the Prometheus query language. It's called histogram quantile. It takes the percent number as the first parameter, a histogram as the second parameter, and it does this for you. And then you can visualize these estimated percentiles in your monitoring dashboard. So this is actually pretty cool. So what histograms allow, they look much better on these hard facts. So you can actually specify the time interval at query time. So I didn't have an example here, but it's really trivial to do this. And as we have seen, aggregation works as well. And you get all the goodness from percentile values because you can just estimate the percentiles based on your histogram. And in addition to that, if you look at the histogram data itself, it gives you information how the distribution is shaped and so forth. So it's actually looking really good. However, most people in practice do not use histograms. And question is why? And the reason is actually that they don't know what to specify as bucket boundaries, right? So if you have a service that you know really well, right? So you know it takes maybe 200 milliseconds, and sometimes it's 50 milliseconds less, and sometimes 50 milliseconds more, then it's fairly easy to set up a histogram for monitoring that service, right? So you know exactly, throw some bucket boundaries in that area, and you will get great data, you will get great information about the latency behavior of your service. However, in most cases, in the real life, you just have no idea. You don't even know, is it microseconds or milliseconds or seconds? I mean, you just don't know how the service behaves. And if you don't know, then you will have a really hard time to specify reasonable bucket boundaries. And then you cannot use histograms. And that's where many people just revert back to using pre-calculated percentiles, because the issue with them is you cannot aggregate them, but at least you get some numbers representing the latency behavior of your service, which is better than having nothing at all or just averages. So there is a new development that tries to fix this problem. So actually the underlying ideas are not very new. So what's new is that this is now implemented and picked up by major open standards like the Prometheus open metrics or like OpenTelemetry metrics and so forth. And the good news is what's done in OpenTelemetry metrics is even compatible with Prometheus metrics and so forth. So it's looking pretty good. The name hasn't converged yet. So OpenTelemetry calls these things exponential histograms. Prometheus calls them sparse histograms or sometimes native histograms. So maybe this will converge in the future. But the underlying idea is the same. So and the idea is you have a histogram with infinitely many buckets, right? So what you see here is an example where each bucket boundary is just double so much as the previous one. So you have a bucket at 1, at 2, at 4, at 8. So it just like with each new bucket boundary, it doubles. Also for the smaller numbers, 1/2, 1/4, 1/8. So with each bucket boundary doubles so much as the previous one. And if you have such a histogram, so the idea is no matter what the order of magnitude is that you are measuring, whether it's nanoseconds or microseconds or milliseconds or maybe years, you will always have a certain number of buckets in your order of magnitude. So that's actually good. Of course, this one here is not a very fine resolution. So if you just double the bucket size with each step, and this is where this schema comes in. So it's called schema in the Prometheus implementation and scale in OpenTelemetry. So I don't know if there will be some common terminology once, but this is what you see here is schema 0. And what you can do, you can increase the schema and then you get double so many buckets. So if you go from schema 0 to schema 1, then you will have one bucket in the middle between two previous buckets. Okay? So middle in terms of this logarithmic scale here. So the middle between 1 and 2 would be the square root of 2. Anyway, but you just get double so many buckets. If you increase the schema again, you again get double so many buckets, like one bucket in between two previous ones, right? And Prometheus supports this up to schema 8. So if you double your number of buckets 8 times, you get a pretty decent resolution. And I actually did the math and tried to figure out, like if you take these types of histograms and calculate, like estimate percentile values based on them, how precise are they? And it's looking pretty good. So with schema 0, it's of course not so great. So you have 33% potential error, but it goes down rather quickly. So schema 5, you're already at 1% potential error. Schema 8, you are at 0.1%. So it's actually looking pretty good, right? So what you might ask yourself if you see this, now don't we again have kind of an infinitely growing data structure because you have this infinite amount of buckets, and if you have many different observations, maybe you have a data structure that can grow indefinitely in memory. And theoretically, this would be the case, but there are tricks to prevent that. So the first trick is you can reset it from time to time and start from 0. The Prometheus server understands that and supports that, so you can do that. And the second trick is you can actually specify a maximum number of buckets, right? And as soon as the maximum number of buckets is reached, then automatically your metrics library will scale the histogram down. So basically it decreases the schema, so you get one schema level less, right? Basically you end up with half the buckets, so two neighboring buckets are just merged into one, right? And then you have a little bit less resolution because your histogram after scaling down has like one level less resolution, but you will not exceed this maximum number of buckets that you have specified. And that's actually nice. So you can decide how much memory do you want to spend, how much do you want to make available for that histogram, and then it automatically adapts and scales down if that maximum number of buckets is reached. So if we look at the evaluation for that one, it's actually looking great in all areas. So it still has the good properties of standard histograms. So you can specify time intervals at query time. It supports aggregations just like any other type of histogram, of course. But the thing is that the need for knowing bucket boundaries is gone away. So you can just throw these things in without having any prior knowledge of how your service behaves, and you can just use them. And also, if you have a good enough resolution, if you have a good enough scale, you can derive relatively precise percentiles out of these histograms. So what's the drawback? There might be none, so I don't know. So the thing is that they are pretty new. So they are currently in the Prometheus server, they are in an experimental feature branch. So if you want to try them today, you need to build your Prometheus server from the sparse histogram feature branch. The same in the Prometheus Java client library. It's also still a feature branch. In the Prometheus server, I think the plan to merge this into main is in maybe 3 or 4 weeks or so. But then it will be a beta feature that you explicitly enable with command line parameters, right? And as you know, with all things in software engineering, if you haven't really tried it in production at a large scale, it might happen that once you try it, it turns out that it doesn't work as well as we have thought and so forth. And so it's a little bit, you still need to be cautious until it's really proven that it's good. But we ran lots of experiments, of course, within Grafana, with our internal services and so forth, and it's looking quite good. And also these things, as I have mentioned, are already part of the OpenTelemetry metric standard. So if they turn out to be useful, they will also be part of OpenTelemetry, and then OpenTelemetry is interoperable with Prometheus, Exponential, histograms, and so forth. So I'm actually convinced that these things will be widely adopted over the next year, over the year 2023. Good. So that already brings me kind of to the end of the talk. So we started off just taking a look at, if you measure durations, what are you actually measuring, right? Highlighting this difference between you're likely measuring service times, and response times might be different and so forth if you have queues. And I showed you this demo with some of the examples. And then we went through a couple of representations for latency numbers, average and maximum, percentiles, histograms, and the new exponential histograms or sparse histograms, or however they are called in each framework, and highlighted a bit of the advantages and disadvantages. What I also have is slides like for popular Java metrics libraries showing which library implements what. So drop wizard metrics, micrometer metrics, the Prometheus Java client, the OpenTelemetry Java SDK, and the upcoming microprofile 5.0. And I actually have like one slide for each of them. But I thought it's a bit, for this talk to just go through all of these and just go down the checklist. It's maybe a bit boring. So what I will do, as soon as the YouTube video is out, I will just comment a link to the slides below the video. And then if you're interested in trying something out, you can just look at the slide for your favorite metric library yourself and figure out what it does. The one thing that I promised you to mention is if you use percentiles with micrometer, what that actually uses under the hood. And interestingly, it uses something that's already pretty similar to exponential histograms. It's called HDR histogram, but that's currently, it's just, used within the micrometer library. The micrometer library uses this to estimate percentiles and then gives you pre-calculated percentiles. So you will not get the raw data, and you will not, be able to aggregate something in your monitoring backend. But internally, it's actually already the thing that will become standard, in Prometheus and in OpenTelemetry metrics anyway, and then you can do these things in your monitoring backend, which is cool because then you can aggregate metrics before you estimate percentiles. So that's all I have. There are a couple of minutes left for questions, really. So if you have any questions, go ahead, and otherwise, good conference. Yes?
I'm doing it in practice, and actually it works. I know it's incorrect, so I'm not saying it's correct, but it's sometimes good enough, let's say.
Yeah, that's so I repeat the question for the video. So the question is, how bad is it really to aggregate things like averages and percentiles? Because you can do this in practice, and sometimes it's good enough. And I mean, this depends on how your traffic is distributed, right? So if you have an evenly distributed traffic across all instances and have similar distributions of latency numbers across all your instances, then if you calculate the average, it will basically, each instance is just representing the overall average. And then, yeah, it's not really wrong to just conclude from that. But if you have traffic that's not so evenly distributed, like you have only 10% in one server and 80% in the other, or maybe one server is having issues and it's much slower, and the others is like taking the vast majority of requests and it's much faster and so forth. So if there's any imbalance, then these errors pile up, and so then it's not correct anymore. So it's basically like, if you do this, in the good case it works, in the bad case it doesn't. But unfortunately, with monitoring, you want monitoring that works in the bad case. So that's yeah. Any more questions? Yeah.
seconds we'll just call good, and anything above a second is bad, and then I can in practice use histograms rather than having to use like that schema back off where like I can't have a guaranteed error bound.
So the question was whether it would be a good idea instead of having infinitely many buckets to just set an upper bound and a lower bound and then have buckets in between because it sounds simpler. And yeah, I think you could do this if you know what your maximum and minimum is. But the implementation of these exponential histograms works in a way that if buckets are empty, they don't take any space or any resources. Only buckets with actual observations take space or take resources. And so there is no difference whether you have an upper bound and everything above is empty, or whether you have infinitely many buckets, but just at some point you have no observations anymore. So if every bucket higher than your maximum observation will be empty and will not take space, will not take any resources. It's just, they are just theoretically there in case an observation comes with a higher value. But as long as no such thing is observed, they will just not take any space. And so there's no need to set an upper bound. Is there any more question? No? Then thanks a lot for listening and enjoy the DevOps.